Hello, I'm back. So now we'll discuss 2.3. And first of all, we want to know what is an even function and what is an odd function. How can we define that? And if a function is given, how can we identify whether it's even or odd? If a graph is given, how can you eyeball and see whether it's odd or even? That's what we want to know first, okay? So the basic definition is, if you replace your x by a negative x, you'll still get the same value for even function, okay? I'll just show one example like that. Let's say f of x is x squared, okay? So what should be your f of negative x? We'll just replace this x by a negative x, right? So this is still going to be x squared, and this is exactly f of x. So as you can see, despite the fact we have replaced our x by a negative x, we're actually getting the same result. So we'll call this as even, okay? And for odd, as you can clearly imagine, if you replace your f of x by a negative x, you'll actually get a negative value of that function. Now, what could be an example of that? Let's say f of x is x cubed. So if you replace your x by a negative x, you get a negative x cubed, right? Which is definitely negative of the functional value of f of x. That's a negative, okay? So that means as you're replacing your x by a negative, you're actually getting a negative value of the same function. So we'll call this is an odd function, okay? That's the basic definition. Now, what about the graphical representation? Okay, now, if a graph, if we have a graph, then we can actually eyeball and say that whether it's even or odd. So first of all, if a function is even, then it's symmetric with the y-axis, okay? Symmetric with the y-axis. And if it's odd, then it's symmetric with the origin, okay? Now, what does this mean? Symmetric mean it looks similar. It looks exactly the same if you just separate that particular part. Now, let's see one graph like this, one graph of each rather. So if you have a graph like this, let's say, oops, okay. So although my picture doesn't look good, let me try once again and see what happens. So this is, hopefully this will work. So now, in terms of the y-axis, which is this one, if you separate these two parts, if you just separate these two parts, as you can see, this part, it looks exactly like this one, right? Just a mirror image of that. So we call that the graph is symmetric to this y-axis. So this is even. Okay, that means look alike. It looks like a mirror image or something like that. Okay, so For odd, let us see one example of that as well. Okay, now, so in terms of, or rather with respect to the origin, which is this one, if you take this part and this part, again, as you can see, this looks like a mirror image, and it is exactly, it does look like exactly the same way, right? Like the same way the curve has gone in both occasions. So we say this is symmetric with respect to the origin, and we'll say this is art. Now, a quick question could be, what if a function looks like this? First of all, uh, that is not even a function, okay? Because simply, if you just draw a parallel line to the y-axis, you can see it intersects this into two parts or 2 points. So this is not a function. No problem. Still, we can find whether this is odd or even, this expression rather, or this relation we might say. As you can see, if we take two parts in terms of the y-axis, on our right we have this, on our left we have this. This is not symmetric, is it? And if we talk about the origin, still we don't have the symmetricity, right? We don't have any symmetry. This is not symmetric with respect to the origin as well. So this is neither odd nor even. Okay, so that's a good example. Because you might be wondering that it has to be either odd or even. No, that's might not be there. So it could be neither of those. Okay. Now, okay. Next up, we want to see what are the basic properties uh, of a function. Okay, so we want to see what is an increasing function, what is a decreasing function, and what's a constant function. Okay, so let's start from here. So if you are increasing your value, that means if your x2 is greater than x1, then if you are getting the functional value bigger than the previous one, or I think I said the other way, I'm sorry. So if you are actually decreasing your value of x, and in return you are actually getting a lesser value, a lower value for the function, the corresponding value of that function is also smaller. That means as you are moving towards your left, that means as you are lowering your x, your functional value is also getting lower. We say this is decreasing. Okay. But if it's, or rather, uh, we might say, we might generalize this as, let me rewrite this. We can actually generalize this as, let me show this all together so that it makes sense for you. Okay. So let's say I'm just doing this. I'm increasing my value. Okay. X2 is bigger than X1. That's your X1. That's your X2. Okay. This is bigger. We are going to our right. If your functional value is also getting bigger, this f of x2 is the corresponding value of this x2. That means you are going to your right, and your functional value is also increasing. So we'll say this is increasing. If it's decreasing, that means you are going to your right on the x-axis, but the corresponding value of that x, the functional value of x, is actually, as you can see, f of x2 is actually less than f of x1. So that means it's actually decreasing. Okay, and if it doesn't really change for whichever value you are taking, if it remains the same, we'll say it's a constant function. As simple as that. Okay. Now, let's see one example of it. Okay. Or we might use uh, the same example to find out all of this. Let me use this. Okay. So let's say that's my graph. That's -4, -2, 0, +2. Okay. That's 1, that's 2, that's 3. So as you can see, as I'm increasing my x from -4 to I'm going to -2, I'm increasing my value of x, right? As you can see, the functional value remains the same. It doesn't really change. It doesn't go up or down. So for that part, that means from -4 to -2, we'll say we have a constant function, right? Okay. Next, as you can see, let me use this from negative to, as I'm increasing my value from -2 to 0, you can see the functional value is going up. It's actually getting better, right? Initially it was 1. Now at 0, it has reached 3. It's definitely on the increase, right? So we'll say from -2 to 0, our function is definitely increasing. Again, as I'm increasing my value of x from 0 to +2, as you can see, my functional value is getting lower and lower, as low as 0 in fact at 2. That means this guy is slowly and slowly going down. So from 0 to 2, we'll say um, this is definitely decreasing. Okay. All right. So from the graph, we can actually see that. Now, we want to see what happens when we try to find a local mean or local max. Okay, let's do this way. If your function is going like this, okay, as you can see, this is going up, 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 and up. And suddenly after this point, it's going down, down, and down. So if it's changing its direction from increasing to decreasing after a point, like this one, before this point it was increasing, after this point it is decreasing, we say that particular point we have, at that particular point we have a local max. As you can see, it does look like a maximum value, right? At this point. We have a peak here. Same goes for this one. It was previously increasing. After that, it has started to decrease. So it does look like a peak point, right? So that's a local max as well. And vice versa for local mean. Let me use a different color. It was initially decreasing, and after this point, it has started to increase. So from decrease, it has started to increase. At this point, we can see we have a minimum point, or it has a lower peak. So we say it's a local mean. Same goes for this one as well, right? So that's how, from a graph, we can actually identify what's the local mean and local max. Let's see one example of that. Let's say we have this. Okay, so that's -2, that's a -3, that's -1, 0, uh, that's 1, okay, that's 2, and so on. That's 1, 2, let's say that's 3, okay. Okay, now if I say find the local mean and local max, can you do that? As you can see, this graph is going down, 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 and after -2, it has certainly started to increase. So we'll say we have a local mean here, and the local mean is at x equals -2, right? Okay, let's move on. At 0, we can see previously it was increasing, and at 0, after reaching this peak, it has started to decrease again. So at 0, oops, sorry, at x equals 0, we have a local max, right? We have a peak point here. It was initially increasing, and after that, it has started to decrease. So that means that's the local max. I forgot to write it. It's the local min. Pardon my bad handwriting. It's getting worse and worse. I'll try to make it as clear as possible. Anyway, let's move on. And at 1, as you can see, it was initially decreasing rather, but after 1, it has started to increase again. And we can see we have a local max, local mean here. So we'll say at x equals 1, we have a local mean. Okay, so that's how we can find local mean and local max. Okay, now what about absolute maximum and absolute minimum? What about that? Because this looks like a local mean and local max, but we want to see what's the absolute maximum and absolute minimum. Okay, now first of all, we want to know the definition. Let's go back to definition. So the definition of absolute maximum is if you have a number within your interval, within a certain interval, for which your functional value is greater or equal your functional value, okay, at that point, for all the other x within that interval, then we say that at that point we have absolute maximum, and vice versa for the absolute minimum. Now this might sound absurd, but if I show you one example, things will be clear, I guess. I'll try to convince you anyway. Okay, so let's say I have a graph like this. Okay, so that point is 4, that's 1, 3, that's 3, 6, and that's 5, 2. Okay, okay. Now, as you can see, for x, we have started from 0 and we have ended at 5. As you can see, this is actually, let me write it for you. This point is 0, 4. So for the values of x, we can actually see that it has started from 0 right here, and ended at 5. So the interval is 0 to 5. Okay. Now within this interval, we want to find a value point for at which it's actually bigger than the functional value everywhere else. Okay. So if we eyeball this, we can see this is the highest peak point, right? This is the peak which looks taller than the rest. Okay. So we'll say that at f of 3 we have a value of 6, which gives us the absolute maximum. And we actually have two minimum values, right? One here and one here. Now, which one is the absolute minimum? That could be the question. Okay. As you can see, for 1, our corresponding value is 3. For 5, our corresponding value is 2. 2 is definitely smaller than 3, right? So we'll say that at f of 5, we have a value of 2, which is giving us the absolute minimum. Okay. Okay. Now, let's say I have a graph like this. One more example on this. Let's say there is a hole here. There is a hole here as well. Okay, that means this particular value is not included in the graph. Okay, this particular value as well. The hole means that at that point we don't have a defined value of that function. Okay, that point is not included. Okay, so let me define the points. 2, 2, that's 3, 5, and that's 5, 3. Okay, and let's say that's 6. We'll soon see why I did that. Anyway, now the question could be, where is your absolute max or absolute min? Where is that? Or do you have any local max or local min? We want to answer all the questions from the same graph. Okay. Okay. First of all, we want to see whether we have a local min or local max. Okay. So this function is actually going on and on. It will not go beyond this line. That's why I've drawn this. We call this asymptotic. So this curve will never go beyond this line, but it will keep going very close to that line. It doesn't stop here. It actually goes on and on, okay? So that means there is no maximum there. As I said, it needs to change its direction from increasing to decreasing. Then we can say we have a maximum there. It's actually going up and up. So that is not a maximum. At that point, we don't have a maximum, right? At this point, we can see that up to this function is increasing. After this, we can see this is decreasing. That's all right. But at that very point, you can see the function is not defined. There is a hole here. So that means we don't have a defined value. If we had a defined value, then this would have been the local max. But as we don't have a defined value, we don't have a local max. We don't have it. Okay. Now let's try local min. So at this point we can see that up to this was decreasing. After this it looks like it's increasing, right? So at this point we definitely have a local mean. So the value of x is 5, so we'll say at x equals 5 we have a local mean. Again, at this point we don't have a defined value, so we're not going to count that anyway. Okay, now what about absolute value, absolute minimum and absolute maximum? Okay, now for absolute maximum you need to have a value at which you have the highest peak. The only peak you can see here on this graph is this. This is the only peak here, right? Because that's going on. There is no peak here. There is no stopping here. So the only peak is this. We don't have a defined value there. So there is no question of having an absolute maximum. Okay. And for absolute minimum as well, we need to have a value for which the functional value is the lowest. So the lowest point here is this one. Again, this is not defined. At this point we have a hole. At that point we don't have a defined value, so we'll say we don't have absolute minimum either. Okay, so that's your uh, absolute max and absolute min. Okay, I'll stop here today. Tomorrow I'll just uh, add two more things, two more little formulas from 2.3. We'll start with that and then we'll continue our regular schedule. Okay, so I'll see you tomorrow at 3:15. Don't forget to join the class. See you tomorrow. Bye-bye.